In our segment decoder, we have our FPGA clock as an input, main input, with a few switches that I will talk about. And our output are basically the 7-segment display, so the cathodes as LED out and the anodes as anode activate. So you should be able to see here we have the FPGA. So as you know, the code is supposed to run between 4 modes. We're supposed to have a set time mode, a current time mode, a 24-hour mode, and an alarm set mode. So for our time set mode, we will be using the rightmost switch, which is called set switch in here. The second switch is to set the minutes, it's called minute switch. The third one is to set the hours, it's called hour switch. Then we have the 24-hour switch, which is called the reg switch in the code for regular time versus military time. Then we have our alarm set switch, which is called alarm switch in the code. And then we have the last switch, which turns the alarm on and off. So we will be talking about the different components of the modes in a minute. Now I will finish walking through the segment decoder. So first of all, we have a 1-second counter that serves to count, to increase the counter every second. So we find that in here, basically splitting up the 100 megahertz clock into 1 second signal that we can then use for the counter. And we tested the accuracy of our second clocks for the extra credit, and it seems to be working very precisely. And I can show you that right now it's indicated here to be 5:51 and 45 seconds, and I can go on the computer and the time is correct. And the FPGA has been running for now approximately 20 minutes. So there is basically no error in our 1-second counter. So just specifying that for the extra credit portion. Then we have our calls for the module implementation of the debouncers. The debouncers will work for the stop switch here, which is going to be to increase the set time or the set alarm. This switch here, which is to decrease it. This switch, or rather, these are all push buttons. This push button here, which is for this is for resetting, and this push button here is for confirming the time. So I will show you this at the end. All right. Now here we have the call for the ALU, and Suyash will talk about the ALU in a minute. And then the output of the ALU is going to be directly the displayed number, which we are then going to be using in here to basically be the output of the segment display. So this is going to be, this is the decoder portion of the 7-segment display that we have written. And we have had to adapt the code for the 7-segment from the previous labs, because this time we are directly using all of the digits on our 8-digit 7-segment display. So we ended up changing this portion from 4 bits to 8 bits, and it works pretty well. So now pass it on to Suyash, who will talk about the ALU portion of our code.
Okay, so I'm going to explain the ALU portion from here on. So basically, the inputs here are the clock, which is 100 megahertz, the reset button, the set switch, the minute switch, the hour switch, and the reg switch. We have an alarm switch. The up and down increases and decreases. This is for the increment and decrement, basically. And then we have here we have the display number, which is of 3-bit. Sorry, which is of 18 bits. The speaker output and the PM output. 1 second. Can we scroll down? So we have a register here, which is an 18-bit register, and it has the current time. The 18-bit wire here has the display number set. So here we are calling the set time, which is here up here, and this basically is one of the modes of the ALU. Here we're calling the alarm time, which is another mode of the ALU. And if we scroll down, so here, what basically happens is that if 1 second enable is equal to 1, then we enter this block. here the current time is increased by 1 minute. In case the second time or hits 59, we'll increase it by 41, so we can increase the minute. And if the current time hits like an upper limit, then the whole thing becomes 0. And the same as for this here. We increase, since we can only increase the hours we by 1. We use this amount of addition to increase it by 1. In this block, if the set switch equals to 1 and the alarm switch, if the alarm switch is equal to 1 and the set switch is equal to 0, the display number is the displayed alarm number. If the set switch is equal to 1 and the alarm switch is equal to 0, then the display number is the set time, basically. If both are 0 or both are 1, then the display time is the current time. So now in this block here, we use this block basically helps us to convert from regular time to the 24-hour clock. And here basically the display time is we take the current time and reduce 120,000 from it to get the display time. And the same is with this block. Finally, we have the alarm module. If the display time approaches the current time, and at the same time the alarm button is on, we will have a speaker output. And if that's not true, if the alarm button is off, then the speaker output will be 0. Or otherwise, if the current time has not approached the display number time, then the speaker output will anyway 0.
We push the up push button and the minutes, which is 0, and the hours, which is 1. Then we're going to be increasing the hours. Once we reach 23 hours, as you can see here, we subtract 23 hours to go back to 0. Otherwise, we just add 1 hour. Then if the minutes, which is 1, and the hours, which is 0, if we reach 59 minutes, as you can see here, we add 4100 so that we get to 1 hour. And then if we get to 59 minutes and we are also at the 23rd hour, then we just subtract 230,000 to get back to 0, or whatever seconds we were at. Let's say we were at 30 seconds, 59 minutes, 23 hours. We will go back to 0000 and whatever seconds we have. Otherwise, we're going to just be increasing minutes by 1. If none of these are true, which means either both of the min and hours, which is a 0, or both of them are 1, well, then we're increasing the seconds. If we get to 59 seconds, we add 41 to get 1 minute. And if we get to 23 hours, 59 seconds, and 59 minutes, then we go back to 0. Otherwise, we just increase by 1. A similar procedure applies for the down switch. So if we press the down push button, min and 0 is 1, hours is 1. If the hours are 0, 0, and we go down by 1, we want to go back to 23 hours. Otherwise, we just want to subtract by 1 hour. If the min switch is 1 and hour switch is 0, and the minutes are 0, 0, then we subtract 4100 to go back to 59 and 59. Otherwise, we just subtract 1 minute. Otherwise, if, again, the min switch and hour switch are both 0 or both 1, if we press the down switch when we are at, let's say, 1 minute, then we subtract 41 to get 59 seconds. If we are at 0, then we want to go down to 23, 59, 59. And if we are in any other case, we're just taking off 1. And the same exact principle applies for the alarm set time. The code is exactly the same because it works effectively and we can effectively change the time. The only difference between the set and alarm time implementation is within our ALU, as we may have already specified, for which we have the presence of this confirm statement here. So only for the set time, once we press the confirm push button, which is the one on the left, then our current time is going to be equal to the set time. I'm going to explain this in a sec.
Here we have the clock in the speaker output in the module, and the input is the clock cycle, and the output is the speaker output. Here we have a clock divider, which is being divided by the frequency and then by 2. And here we have a 17-bit counter. And basically here we keep increasing the tone by 1. And then we go on to the next block. So here, if our counter is 0, then we output the sound, which keeps oscillating between a faster frequency sound and a lower frequency sound. And if not, if the counter is not equal to 0, we just decrease it by 1. And finally here, when the counter is 0, we just output to the speaker.
Time mode. As you can see, I can be in set time mode, but the time keeps running even when I'm in set time mode. And now I'm at 40 seconds. I'm gonna wait. And I'm at 45. So anyways, let's go back to set time mode. We can set the minutes. Let's say right now it's 11:15 p.m. Let's say we want to set the minutes to, I don't know, 30 seconds. Sorry, the seconds to 30 seconds. Then we push the switch for the minutes and we set the minutes to 16. Then we select the hours and we go to 23. It's 11 p.m. There we go. Now we go back to the current time mode. We wait. And we click this button here on the left in order to set the current time to the set time. So let's do it. There we go. Now we want to see if we can switch between 12 and 24-hour modes. Here we go, 11 p.m. 23 hours. If I were to set a time which was below 12 hours, say 11 a.m., set it a.m. So we can see that our 12-hour, 24-hour mode also works. Now you want to set the alarm. Let's say we want to set it for, oh, and by the way, to set the minutes and the hours again, like in set time, we use second button for minutes, third button for hours. Let's say we want to set it to 23 hours. Oh, by the way, overflow goes to 0. Minutes to, oh, sorry. I set the minutes to 18 and the hours to 23. And I could set the seconds, but it doesn't matter. So the alarm time is automatically set. I don't have to press the left switch. And then I can turn the alarm on with this switch over here. Sorry. This switch over here. Wait, so right now we are at 11 a.m., so it's not gonna. Oh, let's go to 11 p.m. Okay. And now dynamics for 18. Set dynamic for 15 and 30 seconds. 15 seconds. Okay, so you might be able to hear this. So we are using earbuds, which I put on the microphone of this iPad to illustrate the working of the beeping sound. We also used an ID, but we figured out the mono output. So as we probably described in the code, this is what we used it for our alarm. So this is our very nice FPGA based alarm clock with 4 modes: current time, set time, 12 and 24 hour, and alarm set modes. We hope you enjoyed our video presentation. Have a nice rest of your day. Thank you very much. Here we have the recording of the audio.